Definition of symmetric relation. A relation R on A is said to be symmetric relation if for every x comma y belongs to R. You observe this point carefully. For every order pair x comma y belongs to R. Earlier, for reflexive relation, what we checked, for every x belongs to set A. But here in symmetric relation, it is not like that. For every order pair in the relation x comma y comma x also present in that relation, then we say that that relation is a symmetric relation. We'll understand this with the help of examples. You observe, I taken set A as 1, 2, 3. You know how to write A cross A. This is A cross A. Now, I'll take one subset of A cross A to check symmetry condition like 1, comma 2, 2, comma 1, 1, comma 1, 2, comma 3. You observe, this is a subset of A cross A. So, this R is a relation on A. When we say this relation is symmetric, to check symmetric relation, we will check for every order pair in the relation. That means you come to this. This is 1, comma 2. For order pair 1, comma 2, for order pair x, comma y, you need to check y, comma x. That means for this order pair 1, comma 2, 2, comma 1 exist in this relation or not. In this relation, 2, comma 1 is there or not, you need to check. You look here, 2, comma 1 is there here. As 2, comma 1 is present here, from this you cannot say that it is symmetric. Why? Because you need to check like that for every order pair in the relation. Okay. Actually what happened? This element passed the symmetric test. For 1, comma 2, 2, comma 1 exist in this relation. This element passed the symmetric test. Like that, you need to check for every order pair. For every order pair x, comma y belongs to R, y, comma x must belongs to the relation. Here you take the order pair 2, comma 1. 2, comma 1 reverse order like y, comma x is 1, comma 2. Is 1, comma 2 is there in this relation? Yes, 1, comma 2 is there in this relation. So this element passed the symmetric test. I hope you are understanding, right? Now come to this 1, comma 1. See, x, comma y, comma x. For 1, comma 1, what is y, comma x? Y, comma x is also 1, comma 1 for this. I hope you are understanding. So here 1, comma 1 for this order pair, 1, comma 1 must present in this relation. Is 1, comma 1 is there in this relation? Yes, here it is. So this element also passes the symmetric test. One important point is this type of elements always pass symmetric test. So whenever this type of element comes, no need to check reverse order 1, comma 1, 1, comma 1 is there in this relation or not. 1, comma 1, 2, comma 2, 3, comma 3, x, comma x, this type of elements always pass symmetric test. I hope you understand what I am saying, right? So this element passed symmetric test, this element also passed symmetric test, this element also passed symmetric test. Like that you need to check for every, right? So here 2, comma 3 is there at the end. For this order pair 2, comma 3, reverse order is 3, comma 2. Is 3, comma 2 is there in this relation? For 2, comma 3, 3, comma 2 is present in this relation. 3, comma 2 is not there in this. So this relation is not symmetric. When it is symmetric, for every order pair x, comma y in the relation, y, comma x also must present in this relation. Then only we say that this relation is symmetric relation. So what I'll write here, I'll name it as this R1. R1 is not symmetric. Why it is not symmetric? Because 2, comma 3 is there in this relation, but 3, comma 2 does not belongs to the relation. That's why we say that this relation is not symmetric. You observe, I taken one relation on this set A. Is this relation is symmetric relation or not? How to check symmetric relation? For every order pair x, comma y, comma x is there in the relation or not, you need to check. So you come to this relation 1, comma 1. See, I said na a x, comma x type elements, a, comma a, 3, comma 3, this type of elements always pass symmetric test. No need to check. You see here, this is like x comma y. Y comma x is also 1 comma 1. 1 comma 1 is there in this relation. Means yes, here it is. Yes, here it is. So this type of elements always pass symmetric test. So come to this order pair. Is it passes the symmetric test? Yes. Come to this 2 comma 2. Reverse order of 2 comma 2 is there in this. This type of elements always pass the symmetric test. No need to check. Yes, this passes the symmetric test. You observe here 3 comma 3. Yes, this type of elements always pass symmetric test. For 3 comma 3, reverse order is also 3 comma 3. 3 comma 3 is there in this relation. So this relation is a symmetric relation. You please observe this relation. Is it is a subset of A cross A? 1 comma 2, yes, it is there. 1 comma 1, yes, it is there. 2 comma 2, yes, it is there. It is a subset of A cross A. So this is a relation on A. Is this relation is symmetric on set A? Is this relation is symmetric on set A? How to check? You will check for every order pair in the relation. For every order pair x comma y comma x is there in that relation or not? You observe here 1 comma 2 is there in this relation. For 1 comma 2, 2 comma 1 is present in this relation. No. So this element fails the symmetric condition. If one element fails, directly you can write this is not symmetric. No need to check at the time these things. As 1 comma 2, for every order pair x comma y in the relation, y comma x also must present in this relation. Here, when you identified there is one order pair x comma y, for that y comma x does not belongs to this relation. In that case, directly you can say that that relation is not symmetric. I hope you understand how to check given relation is symmetric relation or not. As we have a formula for number of reflexive relations, this is the formula for number of reflexive relations. We have a formula for number of symmetric relations also. Total number of symmetric relations formula is 2 power n into n plus 1 divided by 2. In some other class, I'll discuss why number of symmetric relations is 2 power n into n plus 1 by 2.